starting to talk about anyways, that there were applications for differential equations, and that's what I want to talk about today. Some of these are in the book, and your book, and some are from the handout that I gave people who were here last Friday of applications. So let's start over here. This is in the book. If you have resistance proportional to the velocity, you can get a differential equation that will describe the position at any time t after the problem starts. So the beginning point is from Sir Isaac Newton that force is mass, well, it's really the time derivative of momentum, but if you have constant mass, then that becomes mass times the derivative of velocity. Momentum is mass times velocity. And the way Newton said it is right. He said that force is proportional to the derivative of momentum because the mass can change. Of course, we think now from our experience of the last 100 years of getting up toward the speed of light and the mass changing because of what the physics department calls the Lorentz transformation. But actually, even in the world in which Newton lived, he could think of situations where the mass would be changing as well as the speed. And a good example is the anchor, pulling up the anchor, say, for a ship, because the anchor's heavy, but so is all the chain. I can remember when I was in the Army going overseas on the troop transport and looking at the anchor chain that was up on the deck, and I think that the steel and the links was about that big around, and the links were about that long. Well, you got perhaps several hundred feet of links of steel like that. That's a lot. So that's changing as you wind the chain in and pull the anchor up. And the speed at which the whole thing is moving can be changing too. So anyway, as the simplification that we'll do, we'll think of it that it's constant mass, and then our force is proportional to the time derivative of the velocity, and the constant of proportionality here is what we call the mass of whatever it is. Okay, so suppose it's coasting. So this could be as in, say, the homework problem 1, a cyclist who has a mass and the bicycle has a mass and the person and the bike are coasting along. Or it could be a ship coasting in the water, something like that. So for a mass that is coasting, then we suppose that there is a force wanting to slow the whole thing down, so that's why the minus, proportional to the speed that it still has as it's slowing down. So again, you can think of the person on a bike just coasting for a while. So then from our force being mass times acceleration, or dv dt, from Sir Isaac, and the assumption that the resistive force, that's why the minus, is proportional to the speed that's still remaining, we get to write an equation. And you see it involves a derivative, so it's a differential equation. So you separate variables, as you've studied how to do, and then you integrate both sides. And your integral dv over v gives you the log, and your integral here makes this into a t, and you put on a constant. And this is the logarithmic form of the solution. If you remember the differential equations that we talked about last Friday from the handout of examples, we had some where it was this same type of situation where there was a logarithmic form of the solution that came from separating variables and doing your integration. And then, if you can remember back to Friday, I was saying that if you have a logarithmic form, there's also an exponential form, where if you have a log equal to something or other, you could think of taking both sides as exponents on e, and then e to the log v would be v, so then the v becomes whatever's on the right-hand side as the exponent on base e. So that's called exponentiating, if you want a big word. And then you can factor the power. You have e to the minus k over mt plus constant, and then you can, when you have a sum or difference in the terms in the exponent position, you can write it as a product. So you get, because when you multiply powers of e, you add exponents. So then you can write it like that, and then e to some constant is just another constant. So you can write your answer like this. And once you've thought through this drill, you can just go from the log form to the exponential form as something you've memorized. Okay, so you can also see that at time 0, e to the 0 is 1, so the a here is your initial speed, v0 say. So you can say for something of this sort that the solution is always going to be an exponential like this. And if you know the speed at which the problem starts, that's your coefficient. That's the equivalent of your census at time 0. If you thought of this, as we did last Friday, as a population census thing, or as money at compound interest. Well, how far will something coast? Well, what that would be is the time, so say call it capital T to solve for it, at which the remaining speed has dropped to 0. So what you can say then is that this would be a, first of all, think of the displacement, because how far is displacement, s of t. And so v, velocity, is ds dt, where s is the arc length, the distance. So you have something that's moving along the track here, and it starts out with a particular speed, and it gets slower and slower, and it finally comes to a stop. So what we're talking about is how far is that? And so you have to get the connection between speed and distance from the start of the problem. So ds dt. So ds dt then is your formula for remaining speed, which is this exponential formula. So then you integrate both sides here. This is another differential equation. So your s of t then, the v0 and the integral, which you can do. So you have the exponential divided by the coefficient, and complete with the minus sign, so that minus is there, and then the m over k when you divide. So you have that your displacement from when you started coasting related to time is going to look like this. So then this, if you set this equal to 0, you can solve for the c. So the c then will be, if you solve here, will give you the m v0 over k, and then your displacement will be m v0 over k. You take this and put it here and then factor, and you get a formula like this, where the distance is this constant times 1 minus an exponential that is dying out. So then if you take the limit of this as time increases indefinitely, this exponential term dies out, and you have just the coefficient here. So this gives you a formula that you could plug into that would be how far something can coast if it starts out at a speed v0, and if the remaining speed is dying out exponentially according to this formula that we got when we assume that the resistive force was proportional to the speed that it still has. So we can do examples here in just a second. If you're thinking of English units, mass is in slugs, and we can get the relationship between pounds and weight in pounds and slugs by dividing pounds by 32. It isn't exactly 32. 32 is approximately the acceleration of gravity in English units, feet per second. It isn't exactly 32. It depends actually on your latitude on the earth, and to some extent on your longitude and on your elevation above mean sea level, and a lot of things. But 32 is very usable in round numbers. So using that, if you take whatever something weighs in pounds and divide by 32, your quotient is mass and the unit is slugs. And just who decided to call it a slug, I don't know, but somebody in England in the 1700s certainly. And the units then for K, for English units, would be slugs per second, which you'd have to get by experiment. So if it's a bicycle coasting, you'd have to get a value related to what tires are on it and what the surface is of the road, whether it's concrete or tar, or whether it's gravel, and obviously it depends on what the friction is between the tire and the surface.
So I'm sorry, I apologize if you already explained this or if you're going to get to it. Does that include is that all inclusive for all resistance added together, or I mean including air resistance and
that's a good question,
bearings?
And the book isn't really saying.
Okay.
It's just giving you values. What this would have to be is some kind of constant that would be all resistance. So
Okay.
air resistance would be important if you're thinking of something that's going at any particular speed. It would depend somewhat on what the situation is. It'd be a little different if you're thinking of a cyclist, say, where certainly you'd have to think of the K as some kind of a catch-all, both for air resistance and for tire resistance. And I don't know that it would realistically be the same for both. So this is kind of an oversimplification in that
Okay.
sense. If you're thinking of a ship has been at some speed and it's still going, even though you're no longer applying any power, say, mostly that would be a K that's the friction, I think, between the hull and the water, because the ships just don't go that fast. But there'd certainly be a factor of air resistance. So if you're trying to be realistic here, you can get into quite a bit more than you can see that this model is perhaps an oversimplification.
Okay.
Let's say that. But it should be actually all resistance, however you're going to handle it. So if you're doing metric units, then your mass is in kilograms, and then the K would be kilograms per second. So if you look at their problem 1 in 9.3, they talk about a cyclist and his or her mass is 66 kilograms, and the bike is 7 kilograms, the problem says, okay. And the person is coasting 9 meters per second, and that's certainly fast enough that there is an air resistance factor in it. But I think primarily the K the K is supposed to be a composite to take into account air resistance, but I think most of it's really, there is tire resistance probably. And so the question A part is, how far can the cyclist coast? So we can use our formula that we derived, which is the limiting distance, S of t, from the start to where the object stops, is the mass, the initial speed, and a suitable K. And so putting in the total mass, 66 and 7, the speed at which the problem starts, and the 3.9, we get this many meters. So how much time required for the speed to drop to 1 meter per second? Okay, so call that time t. And you see, we have our speed, our formula we got for velocity, on the assumption that the resistive force was proportional to velocity here. So we have this formula here. And using that, we can solve for the time capital T when corresponding to whatever you put in here for the velocity. So when that is 1 meter per second, this becomes 1, and this would be 9, and the K was the 3.9, and the M was the 66 and 7, and then you solve for T. So if you clear out whatever coefficient you have, divide through by it, you have 1/9 is the power of e, then you can take the log of both sides. That's how you solve exponential equations. And so log 1/9, which is a negative number. Remember, it's log 1, which is 0, minus log 9. So I could have said minus log 9 here is minus, because it's a minus sign, this number t, log e, which is 1. So then the t would be log 9 times the total mass of the k value. And that would give an estimate of 41 seconds. I think problem 2 is a little more interesting. This is talking about a big heavy ship. The last 4 of the, well, they were built in World War II, but they really were a World War I thing. The big shootout between the traditional battleship of the 20th century was off the coast of Denmark in 1916 in World War I, and between the British and the Germans, and the British lost 14 ships and the Germans lost 8 ships. So the Germans thought they won because they sank more ships, but the German fleet never came out again, so the British say they won. Anyway, that was the really great shootout among these things, and the ones that were most of them sunk at Pearl Harbor in the end didn't matter that much because it was all a war with carriers and cruisers and so on. But anyway, we built the last 4 of these that we built were the Iowa and the New Jersey and Wisconsin, and there's one more, and I can't think which state it is. But these were big, heavy things. This is 10 to the cube is a metric ton, so this is 51,000 metric tons, and the metric ton is 2,200 pounds. So it's, in English tons, it's a lot of tons, something like maybe 60,000. And anyway, they give a K value, which for a thing like this and a speed that it would ever be going, it would be mostly the friction between the hull and the water, but there would be some air friction. And whether their number is realistic or not, I haven't any idea. They don't say how they got it, and so on. But suppose it is, and suppose it's going 9 meters per second. Well, 9 meters per second is about as fast as a person who is a really good sprinter can sprint at that rate to sprint 100 meters, say, because 9 times 11 is 99, so that'd be like doing 100 meters in just over 11 seconds. And there are people who can do faster than that, but not very many. Okay, so this is a pretty good clip for a person running. It's faster than most people can run. So how far would such a thing coast? So you put your mass and your 9 and your K value in there, and you see you get 7,780 meters, which is more than 4 miles. And this is not so unrealistic, because one of the problems people have with these great big ships is anticipating their maneuvers quickly enough. You have the great example of the Titanic and the iceberg. And by the time they saw the thing, they turned as quickly as the thing would turn, and it wouldn't turn fast enough, so it sideswiped it. And because it sideswiped the iceberg is why it sank, because it was very cold water, and there was a problem of brittle fracture with the rivets and the hull at the water temperature and the impact along the side. It was made so that if it hit something straight on, it really wouldn't sink because of the compartments. But they hadn't anticipated that it would ever sideswipe something and tear out so much of the side of the hull or bash it in, whichever it did, that it would flood several of their watertight compartments. So it did sink in a couple hours, as we know. So that's and then another example is the Exxon Valdez in Alaska. By the time they saw that there was a reef there, they couldn't turn it fast enough not to stay off of it, so on. And so you do have something like this. If you got a big heavy ship, it's going to go quite a ways before it'll stop. So how long to slow to 1 meter per second? So again, you have your exponentially decaying speed, and you want to solve for t. So you can divide through by the v0 and take the log of both sides. So it will be then finally minus the mass over the k, and this log is the log of a fraction less than 1, so it's negative. So you have minus here and a minus here. In other words, your log 1/9 is minus log 9. So you have log 9 and the 51,000 when you've done your division here over 59. And you see it's talking about half an hour that the thing would drift along there. Now, in the real world, it wouldn't be like that because you'd assume that the ship has power and that you could go to full astern and use your engines, your ship to pull you back. But if you were just drifting, and if their numbers are right, this is what it would be. Well, I don't know that either of those examples that's in the book is terribly good, but I think this next one is a good deal more like things that people would do. Mixture problems usually lead to a system of 2 or more differential equations. So this is problem 13 in the book, and what we have is a mixing problem of water with salt in it is what we call brine. So we have 5 gallons a minute of water coming in, and we have 2 pounds per gallon of salt in the water. So this is 10 pounds per minute. You see the gallons cancel as units. So you have brine really at 10 pounds per minute of salt being carried in the brine. And we start out with 100 gallons in the tank, and we have Y pounds of salt dissolved, and the Y of 0 is 50. And we are taking the brine out at 4 gallons per minute, and then we have Y of T pounds of salt over the volume of water in the tank. So the brine then that's going out is 4Y over V. You see the volume is variable because you're coming in at 5 gallons a minute and you're going out at 4 gallons a minute. So the thing is filling, and so there's a limit to how long the problem can run. So your solution would be valid for the time interval from 0 to the point at which the tank is filled. And then the differential equation wouldn't work if you tried to go further, because then it would be overflowing. So we're letting y of t be the pounds of salt at any time t, starting at time 0 when the y would be 50 pounds, but that's changing, you see, because you're bringing brine in and you're also changing your volume. And the V of t is the volume at time t, which starts with 100 gallons and is increasing by 1 gallon per minute. So you really have a system of two differential equations. What I'd call dE number 1 is dy dt, which is the time rate of change of pounds of salt in the tank, which is salt in, which is 2 times 5, 10 pounds per minute, minus salt out, which is the 4 gallons per minute times pounds per gallon, Y over V. And so the rate in minus the rate out is the rate at which the pounds of salt would be changing. So that gets you a differential equation. And then the second one occurs because you have a varying volume. You have 5 gallons per minute in and 4 gallons per minute out. So that becomes 1 gallon per minute, which is your rate out. So dE number 2 is dV dt equal 1. Now, this system, see, there's a system of two differential equations. This one right here, dy dt, is the 10 minus 4y over v, and the v that's here is the solution of this differential equation, for which its derivative is equal to 1. Now, if you have a problem like this, you see, you can solve this one, because you can integrate both sides, and we will in a second. And then you can take the solution from this one and put it there, and then you have one variable, y, and the dy dt. You have a linear first order differential equation. Solve one differential equation and use what you get to replace one of the unknowns in the other differential equation. Now, you cannot always decouple this easily, and as we get across the board, I'll show you a system where it's not that easy to decouple, and with the methods that we have, we can't do it, but you learn to do that sort of thing in the Math 333 class. But this one is decoupled because equation 2 has only the one variable. So solve it, separate your variables and integrate. You have v equals t plus constant, and your beginning volume is 100, because that's what the problem gives, 100 gallons. So obviously the constant is this value at time 0, which is the 100. So your volume then, in terms of time, is 100 plus t. So then if you take the t plus 100 and put it there, the differential equation 1 becomes dy dt is 10 minus 4y over t plus 100, and the initial value is 50 pounds at time 0 salt. Okay, this is linear first order that we talked about how to solve last Friday. And if you move this across, then it looks a little more like what we called standard form if you were here last Friday. Notice your coefficient here is 1. And so you get the integrating factor. Remember what we call P is the coefficient of y when this coefficient is 1. And you integrate that. So you get 4 log t plus 100. And then the integrating factor is what we called mu last Friday. And e to that power simplifies to t plus 100 to the 4th power. So if you multiply your standard form by the mu, the result is what the Bernoullis call exact, which means that the left-hand side is the derivative of the product of the integrating factor and the function y you're trying to get. So the left-hand side is the derivative of this product. It's what the derivative of this product gives you is the integrating factor times the left-hand side up here. See, I actually wrote it out down here. If you use your product rule to do this once again, you have the left-hand factor times the derivative of the right, plus you have the derivative of the left-hand factor, which is 4t plus 100 cubed times the right. So these terms are what this will give you if you multiply here by mu. See, because if you take what's there times that, you have the t plus 100 to the 4th dy dt, which I have here, and then you have the 4 and the t plus 100 to the 4th, and you divide by t plus 100, and that gives you this times y. So the standard form times the integrating factor is this, which is the result of the derivative of the product. And then the right-hand side is the 10 times the integrating factor. So now you can slap the integral sign on both sides here, and it gives you your integrating factor times y on the left, and the integral of t plus 100 to the 4th on the right plus constant. And then you can, what you can do next is you can integrate this. This is a u substitution. So this is u to the 4th du, so you have u to the 5th over 5, and divide the 5 into the 10 here. And then you have to get this constant, which you can do because you have the initial value that the y is 50 pounds at t equals 0. So I've used my initial value in my solution here, and I get these numbers, and I work through these numbers, and finally I get that the constant C2 would look like this, and then put that into the solution up here, and I finally get to something that would look like this. What the book has done is it has taken, it has done some algebra here. So if we try to look through their algebra, let's do that in just a second. I think it's time that I do the sign-up sheets before I forget. Look at how this actually went here. So we get t plus 100 to the fourth y is 2, t plus 100 to the fifth plus the constant, and we put in the values at t equals 0, so that gives you 100 to the fourth, and for y we have 50, so we have 100 to the fourth times 50, we have 2 times 100 to the fifth plus the constant. And so, simplifying the writing, we have the 50 times 100 to the fourth from here, and the 2 times 100 to the fifth, and take that across, so that's your constant. So 100 to the fourth is a factor, then you have 50 minus 200, which is minus 150. So your constant is the minus 150 that this gives you, times 100 to the fourth. And if you wanted to, you can say 150 is 3 halves times 100. So then you have 3 halves times 100 times 100 to the fourth, or 3 halves times 100 to the fifth. I'm doing this to try and get the answer in the form that the book actually has. They've done a lot of messing with this algebra, with these numbers. So then finally, our y from back here is the 2, t plus 100 to the fifth, plus the constant, which is what we have here, minus 3 halves 100 to the fifth, over t plus 100 to the fourth. And then what they've done, they have split the fraction. So if you divide t plus 100 to the fourth into t plus 100 to the fifth, you have the 2 and the t plus 100. And then you have the minus 3 halves, and you have the 100 to the fifth over the t plus 100 to the fourth. So then I take that and I work with that. 100 to the fifth over t plus 100 to the fourth. And what I've done is I've divided top and bottom in green color by 100 to the fourth, which you can do. And I've factored the 100 to the fifth, so that 100 to the fourth will cancel there. And the other thing I've done, you see you have a fraction where you have a fourth power on top, this 4 right there, and 1 there. So you can take this as t over 100 plus 100 over 100 all to the fourth. And that's what this gives you. So these have canceled, and this 100 is this one, and this down here is the 1, this 100 over that one, plus t over 100 to the fourth. And after you've done that, then this 100 over 1 plus t over 100 to the fourth is going to replace this fraction in the answer. So your answer now is 2, t plus 100, 3 halves times the remaining 100 here is 150, and then instead of this, you have 1 plus t over 100 to the fourth. That's the way the book has it. So sometimes you can waste a lot of good time doing hard old-fashioned algebra, but that's what they did. Okay, for better or worse. Well, now let's look at some other examples. If you were here last week, you got a handout that's in my handwriting, which actually goes with the Math 333 class. The ZIL refers to the author of the differential equations book. And the first section of chapter 3 of that book has some applications of linear first order differential equations. If you were here, you remember we talked about the circuit problems and population growth and exponential decay. So who's here that did not get this last week? Who else is here? SW here last week? And, okay, so if you look in this, let's see which one this is. Where I'm going is to this example, and you find it on page 4 at the bottom of the page, where it says a compound interest application follows in my handwriting, and then the problem is typewritten that I copied, of course. And then we have solution there. That's what we're going through here. So we have S of t is the salary, and A of t is the account balance. Now this person has made a deal, which actually is a pretty good deal, and he or she starts out with a salary at time 0 of $30,000, which may or may not seem good, but the person is guaranteed a continuous 2% salary raise no matter what, okay? So it's got to be a government job to get something like that. And also, the person puts 10% of the initial salary, so that'd be $3,000 into this savings account, and they will, the savings account will draw 8% interest year after year, no matter what, which is pretty good. What can you get 8% interest on? And the person continues to contribute 10% of his or her salary to this. So you have a salary contribution, and you have also interest on the account balance, and you also have a continuously increasing salary. And over time, the 2% compound does pile up, and certainly the 8% does. So what we're talking about is what will be the balance in this savings account after so many years, and the idea would be this is the kind of thing it would take to self-fund an IRA that would give you a nice amount of money when you finally do retire. So because what we're told then is the beginning salary is $30,000 and the beginning account balance is 10% of that, which it isn't entirely clear whether the person is immediately to take the $3,000 and put it in this account balance, or if that's put in for him. So you have continuous increase in your salary, so that says the SDT is 2%, 0.02 times the salary balance. You're also told the beginning amount in the account balance is a tenth, so the savings account, so that's 3,000. So then the differential equation for the account balance is dAdt. The account draws interest at 8%, so 0.08A, and it's continuously getting 10% of the salary put in it. So that's DE number 2, and then what the salary is DE number 1. It's starting at 30,000 and getting a 2% raise. So your system is this differential equation and this one. And you see this also is decoupled like the one back here because this DE number 1 involves only the salary. DE number 2 involves both variables, the salary and the account balance. So what you can do is solve this one for S, then put that formula there, and then you get a linear first order equation to solve for the A. So solving DE number 1, then I separate the variables, integrate both sides. So the S of t is constant e to the O2t. So then my constant is S of 0, the beginning salary, which is the 30,000. So then I put the 30,000 there, and this is my formula for this salary with the guaranteed 2% raise. So now I can put that formula in DE number 2 right here, and then I have the dAdt, the 0.8A, the 0.10. That may be hard to read, but it's there. And then the 30,000 e to the 0.02t. Well, the 10% of 30,000 is 3,000. So it's easier to read it down here, maybe. And you see, this is linear first order. And so to get the integrating factor, you remember the P is the coefficient of what would be the A in this problem, complete with any minus sign. So it isn't 0.08, it's minus 0.08. So you integrate that, and then your integrating factor is this negative exponential. So if you take this negative exponential times this line, then the left-hand side will become the derivative of the product of your exponential and A. It will be what the Bernoulli family called exact. So we go over to, where is it? Oh, it's over here. So I'm multiplying both sides of this by the integrating factor, which you see, and then this is the derivative of the product of the unknown function and the integrating factor. And you can check that because you have the derivative of this factor, which is the dAdt times this one, and then you have the A, and the derivative of this, which gives you the minus 0.08, and then I factored out the exponential. So the derivative of this product is there, and that equals the right-hand side. Here you add exponents, so you have e to the minus 0.60. So then you integrate, and here you have the integral e to the minus 0.6t with the 3,000 factored, and so that's your e over the coefficient. So the 3,000 over 0.06 is 50,000, and then you have the minus. So your A is minus 50,000. And then to solve for A, you multiply both sides by e to the plus 0.08 and the constant also. So then to get the constant at time 0, the A is 3,000. So the employer, say, has put the 3,000 into that to start it, and that equals the minus 50,000, and then you see you have plus 0.08 and minus 0.06, so 8 minus 6 is 2, e to the 0.02t at time 0, and then your constant at time 0. So e to the 0 is 1. So finally you have 3,000 equals minus 50,000 plus the constant. So take the 50,000 across and you have 53,000 for your constant. So your formula is 53,000 e to the 08t minus 50,000 here e to the 08t. So the final part of the question is, what would be the balance after 40 years? So you put 40 there, and you put 40 there, and your exponential here is 24.53. It's e to the 3.2, and this one is e to the 0.08, and that's 223. And you see you have close to $1,200,000. So money at compound interest will pile up if you leave it alone long enough. That's the basis, of course, of pension funds. This is the kind of thinking you do if you're working for the state retirement system or something like that. The problem most people have is they can't keep their hands off of it, certainly, because there's always a car to buy or something, right? So anyway, this is a system that we were able to decouple because we could solve the one differential equation here for what the salary formula would be, and then we could use it here in the other differential equation. So the example I want to close with is one where you can't decouple it that easily, and that one starts here and is the one it's in the same set of notes you have. If you go to the next to the last sheet of paper in your set of notes, page 6, and you see the picture, you have tank A and you have tank B. And you get a system because you have the two tanks. And if you look at the picture in your notes, you see you have water coming in to tank A, 3 gallons a minute, and it has some salt in it to start with, 25 pounds if you read the story. And you have brine. You assume this has some kind of machine in there that's stirring the water up so it's well mixed. And you have brine coming out, say, the bottom and on to tank B at 4 gallons a minute. And you also have a return flow from tank B, you see up at the top, 1 gallon a minute. And tank B started out with pure water, but you're running salt water into it, so it doesn't stay pure water. Some of it is going down the drain, you see, and into the water system for Flint, Michigan, of course. Okay, that's what their trouble is. They've got all of the Detroit sewage going into their water system, and some of it is going back into tank A. So what you'll find is when we write the differential equations is that it's not like our example here where you could solve one of the differential equations and take its answer into the other one, or the example that we have here with the single tank where we could solve the differential equation for the variable volume and then take that solution as we did and put it into the other one and get the linear first order. So let's see what you do get. So here's the same picture. So you have 3 gallons per minute coming in, 0 pounds per gallon. It's fresh water, pure water. Okay, goes into the tank, which has salt in it, is mixed. Some goes this way. Well, it goes out this way, and then some more comes in the return flow. So altogether, you have 3 gallons a minute here and 1 gallon per minute there. So it's 4 in altogether and 4 out. So the volume is staying constant at the beginning amount, which was 50 gallons, I think. So what we want is x of t and y of t, where x of t is pounds of salt in tank A and y is pounds in tank B. In the notes, I wrote it subscripted, x1 and x2, but I have a maple handout since I'm using maple to solve the system because we don't have the tools to solve it by hand. And in the maple handout that I'll give you in just a second, I used X and Y because it's easier to use different letters than it is to subscript, just the sheer labor of the typewriting. So I've used X and Y. Okay, so then we skip over to here, and the salt in, you see, is dx dt, 3 gallons per minute, 0 pounds per gallon there, plus 1 gallon per minute, y pounds per gallon from there. And then what's going out is down here, which would be the 4 gallons per minute and the x over 50 pounds per gallon. There's 50 gallons of brine, which continues to be 50 because it's 4 in and 4 out. And for the second tank, the dy dt is 4 gallons per minute in, down here, and x over 50 pounds per gallon, and then going out, there's 1 gallon per minute and y over 50 that's going back that way, and the other 3 are going on into the Flint water system, 3 gallons per minute and y over 50. And so your system then will look like this. If you write this as I have it up here, I have 0 really for this part, but I have 1 times y over 50 there, minus 4 times x over 50 there. But I rewrote this so I had x first and y second to match the second differential equation. So what we have is both x and y in both differential equations. So you need to have some scheme to solve simultaneously. And that's where you use the matrix methods that are in the Math 333 class. So we can't do that, but what we can do is this. I have the maple in the notes that I just gave you, but here I have it in color, and this is a little better take on the maple than it'll be the same graphs, but I have a little more to do it. You use desolve to solve a single differential equation or a system, and then any maple command, after you type the final letter of the word in the command, you put in a parenthesis or a bracket or a brace or something. Now, you're solving a system, you see, so that's why the set braces. And I'm using the capital D to mean derivative, as you do with maple, and I'm calling the two unknown functions, x and y, the way I have here. So what I'm entering really is this differential equation and this one, and then the initial values. So d applied at x applied at t, that's this right here, equals minus 4 over 50 times x, that's this, plus 1 over 50 times y. Notice it's x of t and y of t. You can't just type x and y. They're functions, so you've got to say so, or you'll get a nasty red ink error message. And so I enter the two differential equations, and then I enter the initial values. X of 0 equals 25 as an equation, and y of 0 equals 0 as an equation. So my system is 4 equations, 2 differential equations, and the x of 0 equals and the y of 0 equals. And then you have to say what you're solving for. So the set x of t, y of t. Okay, and if you do that and type it correctly, back come the answers. Doesn't tell you how, but you see number 1 tells you a formula for x of t and for y of t. So then what I did was to define, take the answers and get them in there as functions so that I could get maple to graph them. So I'm taking what it says x of t is, and number 2, line 2, is the function x colon equal t arrow that formula, and then y colon equal t arrow that formula. And then I'm plotting x comma y, and I pick some numbers. I have to give it a domain for t. I can do anything I want, and I can pick colors. So the red will be x, and the y, and the green will be the y, because you see I had x comma y, and then I did red comma green. So the color scheme is in the same order. And the thicknesses can be different, so the x is the thicker of the two when you look at the picture, and you can put a title on it, and you see the red and the green, and indeed the red is thicker ink, and so on. So what's happening then, you see if you read the graph on the back of the page, is that the pounds of salt in tank A, you're running fresh water into this, so, and you're washing the salt out of it over time. because you're bringing in the fresh water and it's going here, and some is coming back, and the rest of it's going down the drain. So gradually it has less salt, and that's certainly what the red graph is showing, you see. Time goes left to right, and the pounds of salt from 25 is dropping from top to bottom. And then the salt builds up in this tank to a point where it's about 10 pounds of salt, but gradually it's washing out too, because what's happening is you're always bringing in the fresh water. So eventually you're washing the salt away. And that's what the two curves are showing, is time, by the time you're at say it's 100, you've pretty well washed all the salt out. Then, if you remember when we started chapter 9 in your textbook, we talked about these graphs, like the graphs on the second sheet of paper, where you have your little slopes and the curves that you can either call trajectories or integral curves as they fit the field of slopes and pass through some beginning point that you specify. So you see what I've done below the picture is I'm giving the differential equations a name so that I can refer to them. And the first one, I could have called it DE number 1, but what I did is little letter D and I subscripted it. So the one is 1, 1 and the other is 1, 2. And then with DE tools, I do the plot, so the two differential equations, and I have different choices of the initial value. The first one I have, x of 0 is 25 and y of 0 is 0. That's what we studied in this problem. But then other choices somebody might have made would be 20 pounds and 10 pounds, or 0 pounds in tank A and 25 in tank B. So I'm showing what happens in the three different cases of assumptions you might have made. And so you see the one curve follows what, if you hold your maple handout up like this, you look at the left-hand side, which is what is in tank B with the assumptions that we made in the problem, and you notice that one of the three curves on the right-hand side is very much the same kind of thing. The other two are different looking curves because we made different assumptions. And then the second thing I've done is some different assumptions yet, and then well, no, it's the same assumptions, but what I did was I colored the curves, so you can tell which curve is which, and on the back page, see there's the yellow and the blue and the green, and if you look at what I typed in the command, you see it says wine color, black, blue, and yellow. So the black goes with the problem like we did it, 25 pounds in tank A and 0 in tank B. And then the blue goes with 20 pounds in tank A and 10 in tank B. And then the yellow goes with 0 in tank A and 25 in tank B. So you can tell in that way on the back which which of the graphs goes with which set of assumptions, which is handy, certainly. So this is how you would use Maple to do something like this problem, which does not decouple, obviously. The methods in 333 that you've learned for a system will let you solve a thing. In other words, you'll learn to do by hand what Maple has done here, but that's as far as we can get with it. So what we'll start with tomorrow is the chapter 11, the parametric equations and polar coordinates, and that'll occupy our time until spring break and probably some of the first week after spring break. And then we'll finish with chapter 10, which is the series and sequences. So that's our plan for the rest of the semester. Okay. So tomorrow, come back tomorrow for some polar coordinates and parametric equations.